She was a girl born into a middle-class academic family in Erlangen, Germany, born in 1882. A Jewish family, although they were not very religious. However, she did go to religious school for a short while, which in fact at that time and place was fairly unusual. And she quickly lost all interest in religion, qua religion. Her father, Max Noether, was a pretty famous mathematician and still fairly prominent in the history of parts of mathematics. If it weren't for his daughter, when people say something like the mathematician Noether, it would be Max Noether, who is well known. But now when people say the mathematician Noether, everybody assumes they're talking about his daughter, Emmy Noether, who ultimately became one of the most important mathematicians of her century. She, at the time when she was a young girl, girls and women were not allowed to matriculate in universities in Germany. They certainly were not allowed to teach. They weren't allowed to be official students, although they were allowed to audit classes. She was of an academic frame of mind, didn't seem interested too much in getting married or doing other things, so she became certified to teach English and French to girls. That was sort of a profession that intellectually oriented women could pursue because there wasn't much else available to them. She took the training, she took the examination, she became certified, but then she never taught a single class because sometime during that interval she became fascinated with mathematics. And she was determined to simply do nothing but learn mathematics. Obviously, she was influenced by her father, who was very tolerant of her interests. But what could she do? She couldn't be a student of mathematics. But she audited classes in her town's university, which is a good, high-quality university where her father taught. And that probably helped or perhaps intimidated the teachers into accepting her as an auditor in their classes, because not every professor, despite warnings from the Ministry of Education that they really could not refuse women auditors, some tried to, but they accepted her. And she would be something like one or two women auditors in the entire university of, I forget their population, but it was very unusual, especially in mathematics class, to see a girl there. Eventually, they changed that rule. Women were allowed to matriculate. They were allowed to take graduation examinations, which she took, and she passed with highest honors. And then she pursued a PhD. So she got her PhD in 1907. I think I remember all the years correctly, but if I'm off by 1 year, don't take my word for it. But I believe in 1907, she got her PhD. Her father had become sick and frail. He had polio when he was a child, and he became less and less able to teach his classes. So eventually she basically taught his classes for him. Although she had a PhD, women were still not allowed to be professors. So she taught his classes without pay, without an official position, because she was there and she had the ability to teach all of them. And he knew that she could, so she wound up doing it, even supervising his PhD students, and so on. Her thesis advisor is named Paul Gordon. He was very well liked in the community, although an old-fashioned sort of fellow, as far as his taste in mathematics went. But he died in, I think, 1914. And you have to understand, the community of mathematicians is not like it is today. Everybody knew each other because it was like a family. There weren't that many mathematicians in Europe, especially in any particular country like Germany. They would probably all know each other. So when Gordon died, everyone, knew about it. And I have to backtrack a little bit. So on her way to her PhD, she had audited some classes in University of Göttingen, which was the I can't pronounce German words either. Just apologize in advance. It was the world center of mathematics. Well, there was more than one center of physics and other sciences, but for mathematics there was no question. It was that university. I'll mention that her home university, Erlangen and Göttingen, were called free universities in Germany, which meant that they were not attached to any church. They were still under government control, but they weren't part of a church. So they had that, I believe, gave them a certain amount of intellectual freedom, which they exploited. Especially Göttingen, especially the math department, under Felix Klein. Some listeners might know his name. One of the top mathematicians in the world at the time, who had hired in 1890 another man named David Hilbert.
Like the Hilbert room, but in Germany, room and space is the same word.
So this is the Hilbert space in the sense, like there's a mathematical object called Hilbert space.
Exactly. And this is the Hilbert space as well,
Yes.
right?
Yes, and in German it's the same word. So in German,
It's Hilbert Raum.
but in German that is the thing. And
To join him at Göttingen. He had not yet attained the fame that he would attain in a few years, but he was sort of a rising star. Excuse me. So they were both there when she audited classes there. She was very impressed with both of them and the other mathematicians there. They made a huge impression on her. Now to jump back to 1914, when her advisor, Paul Gordon, died, he was, of course, a good friend of David Hilbert and Felix Klein. They invited Emmy Noether and her father, Max, because all of these people knew Paul Gordon very well. They invited them to Göttingen to collaborate on writing Paul Gordon's obituary. While she was there in 1914, Hilbert may or may not have remembered her. He probably did remember her because he sort of knew their family and visited them. He had seen her as an adolescent, and he might have remembered her auditing his classes, though we don't know that for sure. But we certainly know that in that visit of 1914, while they were writing the obituary, she made an indelible impression on him because he started talking about mathematics with her and found out that she knew about all of his work, all of his papers, everything happening in mathematics. She had even solved a problem that he had set in his famous, in 1900, his famous set of problems. She had solved one of them. And to solve one of these problems is a major thing in mathematics. There are still some of them unsolved. So during that meeting, he and Felix Klein both invited her to join them, to do research with them. Not to have a job, because that was still not in the cards. That was still against regulations. But just to come there and, find a desk and work with them. Because she had become a specialist in fields of mathematics in which they were working. And there weren't that many people in the world who were at that level, right? But she was obviously one of them. So she joined them around 1915. Her mother died almost right away. So she spent half a year traveling back and forth, arranging affairs of their family, helping her father, and so on. So it was a while before she could settle in to do research, but by, say, the middle of 1915, she was thoroughly absorbed in doing research with Hilbert and Klein at Göttingen. All right, well, first, I think I should mention the reason we're defining these ideas or discussing these ideas is because the central idea of the book is Noether's theorem. She had many theorems, but the one we call Noether's theorem is what's important in physics. And it's a theorem that connects two big ideas in physics and in mathematics. One idea is symmetry, and the other idea is that of a conservation law. So to understand what the theorem does for physics, we have to understand both these ideas separately, and then we can see how they're connected. So a symmetry is an operation that you can perform on an object or something more abstract than an object, say a set of equations, for example, or even a whole theory. An operation that you can perform that leaves everything the same. So the usual examples of symmetry are geometric symmetries, like a butterfly. The operation you perform on a perfect, idealized butterfly is to reflect it in a mirror. And you can't see that anything has changed because it has that kind of bilateral symmetry. The most symmetric physical object is probably a sphere because You hold the sphere in your hand. If it doesn't have any markings on it, it's a perfect sphere. You don't know whether you have rotated it around 2 angles or not, because there's no way to see it. You can rotate it, but nothing changes because there's nothing on or about the sphere to show its orientation. Other geometrical shapes that have symmetry, but in a sense less symmetry, are things like, imagine a square in 2 dimensions. You draw a square on a piece of paper. It has the symmetry that if you rotate it by 90 degrees, you can't see that anything has changed, right? But if you rotate it by other angles, like 20 degrees, it looks different. But if you rotate it by 90 or any multiple of 90 degrees, it has that symmetry that it doesn't change. So those are geometrical symmetries. But you can extend, remember that symmetry is a very general idea where you can, whenever you make any transformation that doesn't change anything, that's a symmetry. So let's jump a level in abstraction from geometry to, say, the way we think about time, for example. So what's important about time is changes in time. You know, I'm this many years old. It means that a certain amount of time has passed since the date of my birth until now when we're sitting here talking. We study history, and different events have years attached to them, right? The War of 1812 happened in 1812. But what does that number mean? It means there are 1,812 revolutions of the Earth around the Sun since some time that we call 0. But what significance does that 0 have? Any physical or logical significance? No, it's just some date and it's changed over time. People have adjusted the calendar. So if you study certain parts of history, it's confusing because the calendar changes during events and so on. So where we put the 0 it's just a convention. It doesn't mean anything. This is a symmetry because if nothing, you know that you can call the War of 1812 the War of 1813 if you decided that 0 was 1 year before and didn't change anything about the war, who won, who lost, or anything else. It just changes that number. This is a symmetry. It doesn't matter where you place the 0 of time. It doesn't change anything. So keep that in mind, because that will return when we talk about physics. So let's think about physical theories. Physical theories, if they describe reality, cannot depend on where you place. They always include time as a fundamental concept, right? Things change in time in physics. That's pretty much what physics is about. What will things be like if things are like this at this time? What will things be like 10 seconds from now? That's what physics does. Where would the planet be a year from now? But it can't matter where you put the 0 of time in your physical theory. And if you look at the equations of physics, like Newton's law of motion, they all have changes of time in them. You never see the variable t sitting by itself, naked and exposed to our gaze. If it did, then the things would change depending on where the t equals 0 is. But that can't be, because it can't have any significance. So this is a symmetry. The symmetry of time is reflected in our physics. Physics can't care where we put the 0 of time. There's a similar symmetry of space, right? If you're buying a sofa and it needs to fit in your living room, you measure the sofa in the store, but you can, and then you go to your living room and you measure the space in your living room, but you know if those lengths agree, you can put the sofa in your living room. It doesn't matter that you measured the sofa in a different place, right? It also doesn't matter where you put the 0 of your measuring tape. You can start with 1 instead of 0 and just subtract 1. It's the difference in marks, the difference in length that's important. In other words, the length of your sofa is the difference of locations in space between one end and the other. It doesn't matter where the end happens to be. So this symmetry is also reflected in physics. You never see in the basic equations of physics a naked variable for position in space. It's always change in position. That's another. These things are so obvious that we don't think about them. Of course, it doesn't matter where you are when you measure something, right? the fact that the equations of physics reflect this symmetry means that it doesn't matter where you do your experiment. If you do your experiment in this room or in the laboratory in the next room over, they should be equally valid. You're still testing the laws of physics, and you don't have to keep track of where you are. Imagine if we didn't have this symmetry, we couldn't really even have science, because nobody could repeat anybody else's experiment because they'd have to go to it the exact same place. This is not the same as saying that all places are the same. Of course, it does matter where you are when you do the experiment, because, for example, the other laboratory might have a different gravitational field, it might be on a different floor. But when I say the symmetry of space, I mean, when you remove all these physical influences that we know are there and are left with just bare space, then it can't matter where you are. It can't. Because if it did, you couldn't have a science. Couldn't have physics, at least. Maybe you could have economics, I'm not sure. So this is a symmetry that's so obvious we don't think of it consciously. It's just too obvious to think about, right? Another symmetry is called the isotropy of space. It doesn't matter what direction you're pointing, the laws of physics shouldn't care. You can do your experiment in the lab, or your lab could be facing a different direction and the experiment should come out the same, as long as what you're measuring doesn't explicitly depend on direction. If it depends on the Earth's magnetic field, then that's an influence that is sensitive to direction. But that's not what we mean. We mean that when you remove all those influences, it can't matter what direction you're facing. So these are all symmetries, and they're all important in physics. But up until Noether's theorem, we didn't, they were obvious. We didn't think about them. We knew that if we wrote down equations and they violated those symmetries, something must be wrong. So we made some mistake. But once everything satisfied the symmetries, they didn't do anything. They were just obvious, right? Have I explained what symmetry is well enough, you think? Okay. It's not always clear to me, because in a sense these ideas are too obvious to explain, because they're a part of our intuitions. Time and space just work this way, so we don't think about it. But when you're writing down equations, you sometimes do have to think about these things. So that's one set of ideas. The other set of ideas is called conservation laws, and that's simpler, I guess. A conservation law is some quantity that does not change as the system evolves in time. So now we're separating out the time variable as being important. The one that people mostly know about is conservation of energy. We learn in school, if we take high school physics and so on, that if you have an isolated system, say the Earth going around the sun, and imagine that there are no other planets and no comets flying by, just the Earth and the sun in space by themselves. That's a well-defined physical system and just a gravitational field. And there will be a certain energy. There's energy of motion of the Earth whizzing around, and then there's a gravitational potential energy that depends on the distance between the Earth and the sun. And you may know that those orbits are not perfectly circular. They're almost circular, but they're elliptical. They squeeze in a little bit. And sometimes we're a little bit closer to the sun, and sometimes we're a little farther away. Those differences in distance between the Earth and the sun translate to differences in what we call gravitational potential energy. So you move closer to the sun and your potential energy goes down a little bit, but your motion goes up a little bit. And the two combine in such a way that the total energy, the sum of the two kinds of energy, never changes. And you can use that fact as a convenient way to solve problems. You can say, without even knowing the equations of motion, great thing that when physics students learn this, they think, oh, this is great. If you tell me what the speed of the planet is here, and then you ask me what the speed is in this place in the orbit when it's a little closer to the sun, I can calculate that without even knowing the law of gravity, without even knowing Newton's laws. Just knowing that energy is conserved and what energy is, and how to write down the formula for energy of motion called kinetic energy. You can just calculate it. It's very simple. So conservation laws are incredibly useful in physics. Energy conservation is one of them. There's also momentum conservation. If you play pool or billiards, and you have all the balls have equal masses. If you hit one ball with another, the white ball that you hit will come to rest, and the ball that it hits will fly off with the same speed. If the first one comes to rest, then the second ball will go off with the same speed. It has to, because the speed is the only equation I'll give you. The speed is the mass times the momentum is the mass times the velocity. So if the masses are the same, if momentum cannot change, momentum of the whole system, then the velocity has to be the same. So you can solve problems with billiard balls, all kinds of problems, by knowing about, if you know about conservation of energy and conservation of momentum, you can solve tons of problems without doing very much mathematics. So we physicists knew you can prove conservation of energy and momentum from Newton's physics, Newton's laws of motion, but conservation of energy, for example, was sort of known in other fields like electricity and magnetism, and more complicated once you get beyond simple planets whizzing around. It was known sort of empirically. It wasn't known why it was true, but it seemed to be true. And it was so widely accepted that it was sort of considered a law of nature that couldn't be violated, although it wasn't clear where it came from. So we have conservation of energy and momentum, and there are a bunch of dozens and dozens of conservation laws. When you get to particle physics, it comes with its own set of conservation laws, and so on. So those are conservation laws. What Noether's theorem did, so up until 1918, when Noether's theorem was published, everyone knew about symmetry, and all physicists knew about conservation laws, but there was no particular connection between them. And what the theorem shows is that those two concepts, those two separate facts, are the same fact. Not that you can derive one from the other only, but you can derive symmetry from conservation and conservation from symmetry. She proved the theorem and what we call its converse. That means that those ideas are really the same idea. That when we say conservation of energy, we are saying symmetry in time. And when we say symmetry in time, we're saying conservation of energy. In fact, the theorem gives us a definition of energy that we had never had before. We never had a definition, what is energy, that works across all fields of physics. It was sort of ad hoc. When Maxwell introduced the idea of an electric field and magnetic field, people worked out what the energy had to be in those fields. Those fields themselves have energy. You can write down a formula, the energy of the field, and then it's combined with the energy of motion of particles, it participates in the total conservation of energy. But you had to sort of, why is that the energy? Because it works, right? But Noether's theorem tells us what energy is. Obviously, in Maxwell's theory of electrodynamics, electromagnetism, that respects the symmetry of time. And her theorem shows that, that is energy conservation. So what is energy according to Noether's theorem? It is that quantity which is derived from the symmetry of time. So if you have a brand new theory, say a new theory of the universe, a new theory of the cosmos or of elementary particles, whatever your crazy theory is, you can write down the theory and you can say, what is the energy in this theory? Well, who knows? You wouldn't know. But if you know Noether's theorem, you say, okay, let's, I'm not going to use the technical language, but it obviously, here's the time symmetry in the theory, and I go through her machinery, and out comes a formula. This is the energy of the theory. If there is no symmetry in time, and there isn't always, if there is no symmetry in time, it's not enough to say that there's no energy conservation. If there's no symmetry in time, there's nothing that you can call the energy. Remember, because energy is symmetry in time. So, for example, you might have heard that the universe is expanding, right? The cosmos is expanding. Because it is expanding, That means not that in the sense that, say, you imagine everything around you is moving away from you. It's not the expansion in the sense that the distance between objects are increasing in a static universe. It's that the space-time itself, the structure of space, is the rulers that we use to measure space are getting constantly longer. What does this mean? If the space-time itself is expanding, then we suddenly don't have symmetry of time, because it actually matters when you do your experiment. Here on Earth, if you do an experiment now and tomorrow, you don't have to worry about this, because the expansion for a lot of reasons. One is that it's insignificant in our lifetime. But if you look at the whole universe and the history of the cosmos, you have to take into account the fact that space-time has been expanding since the Big Bang. Since the structure of space-time is changing, we don't have time symmetry, and therefore there is no energy that we can define, and there's certainly no energy conservation. So what we learned in school, that the energy is conserved, is actually not true when you look at the whole universe. The whole universe is expanding and energy is not conserved. In fact, there's no consistent way to even say what the energy is. Other things are conserved, and Noether figured out what those are, but they're not the simple energy that we learn in classical mechanics. So that was an example. All of that long conversation was an example. One example that you can derive from her theorem, the conservation of energy and the symmetry of time. I've also mentioned symmetry in space, and her theorem shows that that's equivalent to conservation of momentum, and symmetry of isotropy of space, or the symmetry of orientation in space, leads to, or is identical with, I should say, conservation of angular momentum. That what is conservation of angular momentum? I neglected to mention that. If you've seen an ice skater spinning around, and then she pulls in her arms and spins faster, that's because she has to in order to conserve her angular momentum, because the angular momentum has various terms. One is how fast you're spinning, and the other is the distribution of mass away from the center of mass, the center of rotation. So if you pull your arms in, you're bringing some of the mass closer to the center. So to keep everything conserved, you have to spin faster. That's why that works. But that's the same as isotropy of space. So Noether's theorem, it connected these two historic ideas, symmetry and conservation laws. And it wasn't just of academic interest. Oh, that's interesting. These things that we thought were different things are the same thing. It means you can use it to find new physics. So this became, in her lifetime, nothing much was done with it, because we didn't have, new physics had not arisen yet. But like 20 years after she died, particle physicists began to do experiments with accelerators, discovering new particles, kinds of interactions and forces that were new in physics. And they turned to, I will say, special cases of Noether's theorem to say that, it looks like these particle interactions have a certain symmetry. At this point, it becomes a very abstract mathematical symmetry, but it's still a symmetry. If they have the symmetry, I know something about Noether's theorem. I know that means there must be something that's conserved that we might not know about. So you work through the math and you say, this symmetry means that according to Noether's theorem, there's this conservation law, but this conservation law can't be satisfied unless there's some other particle that we haven't found yet. So you use Noether's theorem to predict the existence of particles that haven't been discovered, and then those particles were discovered in further experiments. So it became the basis of what we now call the standard model of particle physics, which is our theory of matter and fundamental interactions. It's all based on this one mathematical idea of hers. She's a kind of person that I think has basically become extinct in the modern university. And if you've had any contact with academic departments, it'll be very surprising to hear about the things that she did, because she evinced a kind of generosity that I have never seen in my career in physics. I've never seen anything like it. Maybe mathematicians are better, I don't know, but I rather doubt it. So let me give you just one anecdote that really explains everything that you might want to know about her, at least about her generosity. So she had, at one point during the 1920s in Göttingen, she became, so I have to explain that she finally got, after a long struggle, mostly a long campaign waged by David Hilbert almost alone in her behalf to get her at a job. She finally was hired in 1919. At the end of World War I, Germany relaxed a lot of its laws, started to permit women to have professorships. And so reluctantly, they gave her this job in 1919, which meant she was allowed to be called a professor of some sort. There was no official salary for her. Can I just tell this one amusing anecdote before I talk about her generosity? It's about David Hilbert. I wouldn't say her mentor. She was too advanced to have a mentor, but her colleague at Göttingen. So when he finally succeeded in getting her a job, it came with a letter from the Ministry of Education saying that this job comes with no salary. It comes with no civil service. You're not in the civil service, unlike every other professor. You're not in the civil service, no pension, no benefits. And it made a very clear note in the letter saying, and this position has no authority over any other employee, all of whom were male. So they wanted to be very clear that Emmy Noether would not have any type of authority over any man. But she was not rich. She had a small inheritance. She had to live, and Hilbert knew this. So he knowing that she was not legally permitted to receive a salary, nevertheless applied for a small salary to the mathematics department for the teaching of algebra, not mentioning that this was against the rules. And they didn't know that because they had not seen the letter from the ministry because he didn't show it to them. And they agreed and paid her the small salary that she received during her time at Göttingen. So that gives you some idea of the personality of David Hilbert. Now, the anecdote about Emmy Noether. So she rapidly got her job in 1919, and during the 1920s, rapidly became the center of her own school of mathematics. A bunch of students around her, and she taught various areas of mathematics. But one area where she became prominent, or probably the leading figure in the world, is abstract algebra. So, at one point during her time in the 1920s, a student, later was to become quite famous as a mathematician, but a student came to her very excited. Look, Emmy, I proved this new theorem. What do you think? And she said, oh, that's very good. Excellent work. Yes, indeed. And she had some suggestions. Well, yes, you need to write a paper, and he did it. And then she said, oh, okay, this is good. You could organize it a little bit differently. Just reorganize the paper a little and then submit it. And he did submit it. It was accepted and published. She became actually the referee for the paper. They sent it to her to review because it was one of her areas of expertise. And so he's very happy. Later on, this student told another student about his result, and they talked about it, and he said, oh, but I was in Emmy Noether's class a year, 2 years ago, and she showed us this exact same result that she had proved. I guess she never published it. And then he thought, how did this happen? And he realized that she decided to let him have it. Instead of saying, oh, I already proved that, she let him go. She even helped him write the paper better. And he was so happy about his results. She didn't want to disappoint him. This is already known because it hadn't been published. So she could pretend that it was new and let him think that it was new. And he could not believe that someone was so generous and cared more about his happiness and his development as a young mathematician than any credit that she might receive from what was, after all, a pretty important mathematical result. She did this repeatedly. There are other anecdotes of she would, to help a student begin almost always his career, she might give him a theorem. Here's a theorem for you. Maybe you can clean it up a little bit and publish it. Okay, I'll publish it and put your name. Don't put my name on it. This is yours now. This is what I mean when I say that I've never encountered, this is an extinct kind of creature. In the modern university, everyone is, if you prove that 2 + 2 = 4, you wonder whether anyone else has proven that, and you try to publish it. No one shares credit for anything with anybody else. In fact, they steal credit. It's more likely that if you pick a random professor in an academic department, it's more likely that he'll be stealing your result rather than giving you a result. It's not pretty. It's not an attractive personality type, I would say, with exceptions. I know some very fine people who are professors, but on the whole, this kind of generosity of spirit, I was amazed when I researched Emmy Noether's life and realized what kind of a person she was, because it was a kind of phenomenon that I had not encountered in my life, certainly. Yeah, and completely single-minded about mathematics. She seemed not to really, she only seemed to care about two things. I've read every letter she wrote and everything, and there are only two things she ever thought about or wrote about: mathematics and helping people however way she could, even in their personal lives, even when it was sometimes not welcome. But my reaction to learning about her life was that, most people would be fed up, and most people would have not tried to pursue a career in mathematics when everyone was saying you can't do it. And the ridiculous obstacles that she encountered, one after the other, every step of the way in her career, including after she escaped to the United States. There were always obstacles in her way. Although her colleagues always appreciated her, these obstacles were institutional and cultural. They were always in her way, but she never seemed to be bitter about them. She never complained about them. She just sought every opportunity that she could find simply to study and teach mathematics, which is the thing that kept her alive and the only thing that she really cared about. So, as you say, she had a tremendous sense of humor. She's famous for that, for laughing loudly all the time. So that's why in the book, by advising my readers not to forget to laugh. That's wonderful to hear. It's been a pleasure talking with you, and I look forward to somehow having a copy of the Polish edition in my hand someday, soon.